2.6 Combination of Functions, the composite functions. We're going to learn how to add, subtract, multiply, and divide functions, find compositions of functions with another function, so we'll find one in relation to the other. And we'll use combinations and compositions of functions to model and solve real-life problems. That'll be coming in lecture. But for the tutorial, we're just going to look at these basic properties here. Now, the sum and difference, product, and quotient of functions. We'll let f and g be two functions with overlapping domains. Then for all x values common to both domains, and this is big, okay? They have to be common, so we'll have to look at each domain individually in both f and g, and then see what's common to both of them. Now, if we're just doing a simple sum and difference, there's nothing to it. You're just going to combine like terms, like always. Now, just keep in mind that if you are subtracting, you are going to have to change the signs of the secondary function that you'll be subtracting. So if we look at this, the solution is kind of clear. If we add f and g, so if we're taking the functions f and g relatable to x, we just take their relative outputs and add them together, which is what we're doing here. So it looks like the answer here is 4x squared plus x plus 2. If we go on to the product, I've just given another, you know what, I should be using the same ones, but it just takes too long to do, so we'll just use these two here, a new f and g function. So what we're saying in the product, f and g of x, is the product f of x times g of x, or the outputs. So I've written it out here. Now you can FOIL it if you want. I'm just going to use the classic multiplication just to remind ourselves about it and do it out. So this would be x to the fourth plus 3x minus 2x cubed minus 6, and then just add them all up, x to the fourth, and I'll make sure that I put it in standard form, so I'll just put the x cubed next, so that'd be negative 2x cubed. It doesn't appear that we have any x squares, so it's 3x minus 6. So all of this does equal this as well. Okay. Now with the quotient, if I just have well, we're going to learn about it soon enough anyway, but synthetic division and long division, we're going to have to do it later to find factors and zeros. But in the quotient, the only understanding that you really need to have at this moment is just when the g of x cannot be 0. Now, there's a couple fundamentals here. If we ever want the whole quotient to be 0, all we have to do is set f of x equal to 0. If we want to know what the domain cannot be equal to, we set g of x not equal to 0. This will tell us all of the values that will not be accepted. Okay. Now, as just a reminder here, I mean, I can give an example, but it doesn't really. So x squared plus 2x plus 1 divided by x plus 1. That's a nice one. You'll find out later. But actually, you could do it. You could factor it out and then cancel it. But let's move on to the composition of f and g. So what we have here is the notation for the composition of f and g. So how we read it is f of g, so f of g of x is equal to f of g of x, and we just use g of x as the first input. Alright? So let's do an example. But before we do, just be careful about domains. And just be very careful, because the domain of f, and the domain of g to have some common ground. Okay? So here we have an example, and what we're going to do is we're going to find a bunch of things out about it, but the very first thing that we're going to do is find f of g. Then we're going to find g of f. Okay, those will be the two main things that we're going to be looking for. But in essence, we're also going to be asked about domains. Okay? So before we begin, it just makes sense to look at the domains of each one of these. I'm going to start out with g of x, and we're going to look at this at very simple, and it's a polynomial function, so we know that the domain is the set of all real numbers. Now with f of x, it's a little bit trickier, right? Because it's a square root. And there aren't any ways to have the same number that's negative multiplied and produce a product that is also negative. Because the fundamental fact is that two negatives, when multiplied together, will produce a positive. So there is no way to multiply two negatives, especially being the same number, to get another negative. But with f of x, what we have to do is, and I shouldn't have used zeros, I should maybe use arrows here. This is a radical, right? So that just means that we have to set the radicand greater than or equal to 0, which then states that we have x has to be greater than or equal to negative 4. So the domain in this case, if we looked at it as an interval, would be the lower value of, we could equal it here, so we should use the bracket. And it could be negative 4 all the way up to positive infinity. Okay? So, with that case here, we can now start to do the composition. So in order to find, and we'll do this independently, but if we want to find f of g, what that means is, remember, f of g of x. So that means that we're going to have to do what? We're going to have to input the expression g of x into f of x. Okay? So what that would look like here is f of g of x. Well, g of x is x squared. So when we put this in, it looks like we'll have, wherever the x is, remember, we're just, maybe I should use a different color. Wherever the x is, we're going to be placing an x squared. So that means that we have, maybe I'll use parentheses, even though we really don't need it here, x squared, and I'll use black plus 4. So all we did was input x squared into the function here. So therefore, it looks like f of g of x, in this case, x squared, is going to be equal to the square root of x squared plus 4. Now, when looking at this, we do have to maintain the domains. So let's take a closer look at this domain. So possibly the easiest way to look at the domain here is to look at this under the radical, or the radicand, here as a polynomial function. So it looks like the domain for f of g of x is actually the set of all real numbers. Which is really nice, because any number that you pick, right, and you can just think about this logically, negative 1 will work, right, because negative 1 squared will always give you a positive. So any number that you pick is going to work out in this example here. So we now know that this shares the same as g of x. Alright, now if we go in reverse, let's see what happens. So if we find not f of g, but g of f this time, And maybe I'll make it look nice there. So that means that we're taking g of f of x, which means that our input is going to be f of x this time. And that means that we're going to have g of, what was it, square root of x plus 4 input into g of x, which was this. Now, if we take a look at this, it may look a little interesting that you might want to say it's all of the real numbers. But let's take a closer look. So if we look at the domain, here of g of f of x, and then what we can see here is that, yes, it does look like it might crunch down into a nice value, but we still have to take the square root before we can square, right? So in order for this to occur, we know that the domain for this has to be that x has got to be greater than or equal to -4, right? Because of the radicand. We can see that again, x plus 4 is greater than or equal to 0, or x is greater than or equal to -4. So by looking at the composition, it's easy to see that we can make one new function by the composition of two functions. And we can actually decompose these as well. But for right now, let's move on to the bacterial count. And what I'm going to do is I've left everything here for you to figure out. And we're going to talk about this one in lecture in a little more detail.